Now, a slightly more advanced theory of bonding is known as molecular orbital theory. This has a lot of very common themes with valence electron theory that we just discussed, but it really shows us a little better insight as to what happens to the electron orbitals when they do overlap. Now, it turns out that two things can happen when electron can overlap. Because of the wave-particle duality of electrons, it turns out when the electrons get near each other, they can be either in phase or out of phase at portions of the time, so they can result in constructive interference or destructive interference. And what that occurs, if the overlapping of electrons causes constructive interference, it produces a bonding orbital which lowers the potential energy of the interaction. If they produce destructive interference, all that does is create a higher potential energy, and we call that an antibonding orbital. The shapes of the orbitals change slightly, whether they're constructive interference or destructive interference. You can see that antibonding orbitals look like this, and they have a node in the middle usually. Bonding orbitals will take on a slightly different shape as well. But the big point here is that antibonding orbitals raise the energy of the interaction, the potential energy of the interaction. Bonding orbitals lower that. We'll denote whether it's a bonding orbital by showing the orbitals that overlap. In this case, 1s produces a sigma bond. We'll give the antibonding orbital the same distinction, sigma 1s, but we will show an asterisk to indicate that that is an antibonding orbital. Okay, so when two electrons in two orbitals overlap, we can show that with an molecular orbital diagram, which is shown here. One hydrogen atom is going to overlap with another hydrogen atom. It turns out that if, and this will of course result in a antibonding orbital and a bonding orbital, and when hydrogen molecule is formed, both electrons can occupy in the bonding orbital, which is lower potential energy. None of the electrons have to go up to the antibonding orbital. So the result is that the hydrogen molecule is lower energy than the two individual hydrogen atoms, and so it's more stable, and that's why a bond can occur. If we look at this from a very simple mathematical point, we can calculate what is known as the bond order. And what we're going to do here is we're just going to subtract the number of electrons in the antibonding orbital from the electrons in the bonding orbital, and then divide that by 2. If we get a positive bond order, and for hydrogen, first example, 2 minus 0 divided by 2 is positive 1, that will predict that this molecule would be stable. So if we take a look at a helium molecule, He2, we can see that, of course, when the electron orbitals overlap, they're going to produce a bonding orbital and antibonding orbital. This would cause, because helium now has 4 electrons overlapping, cause 2 to go into the lower energy bonding orbital and 2 to go into the higher energy antibonding orbital, producing a bonding order of 0, and this would result in a non-stable molecule, and of course we know that there is no He2 molecules found in nature.